Right now, as you listen to this, you're hurtling through space at over 800,000 kilometers per hour. You can't feel it. You've never felt it, but it's happening. And that's just the beginning of what you don't know about where you actually are. Hello and welcome to the 67 Sleepy Facts channel. Tonight, we are going to dive deep into theories, facts, and stories of our galaxy. You think you live on Earth, and you do, but Earth is just a passenger, a tiny speck riding along in something far grander and far stranger. You live inside the Milky Way, a galaxy of 400 billion stars held together by invisible matter we can't see, spinning around a supermassive black hole we can't escape. And right now, scientists still can't agree on some of its most basic features. We don't even know how many spiral arms our own galaxy has. We can map galaxies billions of light years away with exquisite precision, but our own home? It's partially hidden from us, obscured by our position within it. We're like ants trying to map a continent while standing in the middle of a forest. But here's what we do know, and it's extraordinary. The Milky Way is eating other galaxies right now, in real time, pulling them apart star by star. It's already on a collision course with Andromeda, set to merge in 4.5 billion years. Some of its stars are older than the galaxy itself, cosmic refugees from galaxies that died before ours fully formed. And scattered throughout are rogue stars, ejected by the central black hole at such impossible speeds they'll escape into intergalactic space and drift alone. Tonight, we're going on a journey through these hidden mysteries, from the warped disk you can't see to the dark matter holding everything together, from stellar streams marking the deaths of ancient galaxies to the peanut-shaped bulge at the core that defies explanation. You'll discover why most of what you think you see in the night sky is actually invisible, why the galaxy shouldn't exist according to the laws of physics, and what scientists mean when they say our galactic home is still growing. This will be a long, gentle drift through cosmic secrets, perfect for rest, for wonder, for letting your mind expand while your body relaxes. Some of what you hear might surprise you. Some might challenge what you thought you knew, and some will leave you with more questions than answers, because that's the nature of the universe. The more we learn, the more mysterious it becomes. So settle in. Let your breathing slow. Let gravity soften around you, because we're about to explore the hidden architecture of home, the vast, dark, spinning mystery you've lived inside your entire life without ever really seeing. Let's begin our journey through the Milky Way. The Milky Way has already collided with other galaxies, and it will again. Our galaxy may feel like a stable home, but it is built from the wreckage of others. Over billions of years, the Milky Way has absorbed smaller galaxies, drawing them in, unraveling them, and scattering their stars into tidal streams that wrap around the disk like ghostly ribbons. One such galaxy, the Sagittarius dwarf, is being pulled apart right now in real time, its stars stretched across hundreds of thousands of light years as tidal forces tear it to pieces. And far off in the night sky, Andromeda is drifting slowly closer, pulled by gravity across the void. In about 4.5 billion years, the two great spirals will merge in a cosmic collision. But here's what's fascinating. Stars will almost never hit each other. Space is so vast, so incomprehensibly empty, that even when two entire galaxies interpenetrate, individual stars pass by each other like ships in a cosmic ocean. And yet, the galaxy's shapes will change forever, folding into a new form, vast and quiet. The spiral arms will be destroyed and reformed. Gas clouds will collide and ignite with millions of new stars. The supermassive black holes at each galaxy's center will spiral toward each other over billions of years, releasing gravitational waves that ripple through space-time itself before finally merging into a single, even more massive singularity. Some astronomers have named this future galaxy Milkomeda or Milkdromeda, though of course there will be no one around to call it anything. The Sun will have already entered its red giant phase by then, likely consuming the inner planets. But the dance itself, the slow gravitational waltz of two island universes becoming one, will reshape this corner of space forever. Even galaxies are not eternal. They evolve, collide, and begin again, like everything else in a universe that refuses to stay still. Some stars in the Milky Way are older than the Milky Way itself. Not every star in the Milky Way was born here. Some halo stars, ancient, metal-poor, and wandering in long, tilted orbits, appear to have formed even before the Milky Way had fully taken shape. Astronomers believe these stars may have originated in smaller primordial galaxies that merged with our own billions of years ago, absorbed and scattered, but never truly destroyed. Their chemical fingerprints show almost no heavy elements, suggesting they were born shortly after the Big Bang, when the universe contained only hydrogen, helium, and traces of lithium. These ancient wanderers move slowly and high above the galactic plane, like elder spirits from a time before spirals, before order, before the universe learned how to make galaxies as we know them. In their light, we see a universe that was younger, wilder, and still learning to become what it is. Some of these stars contain less than 1/10,000th the iron content of the Sun. They formed in an era when the cosmos had not yet been enriched by generations of supernovae, when metals, anything heavier than helium in astronomical terms, were vanishingly rare. Think about what this means. These stars witnessed the formation of the Milky Way. They watched as streams of gas and dark matter began to coalesce, as the first galactic structures took shape, as the universe slowly organized itself from chaos into the cosmic web we see today. They are time capsules, frozen in composition, carrying within their spectra the chemical signature of the early universe. To study them is to peer back across nearly the entire history of the cosmos, to see in their dim red light the face of creation itself. Our solar system orbits the center of the Milky Way at over 828,000 kilometers per hour. That's more than 230 kilometers every second, faster than anything humans have ever built by orders of magnitude. And still, it takes about 225 million years to complete just one loop around the galaxy. This vast orbital period is called a galactic year, and it dwarfs every timescale we're familiar with. In Earth time, we've only gone around the Milky Way about 20 times since the solar system formed 4.5 billion years ago. When the first dinosaurs appeared on Earth, we were in a completely different part of the galaxy. The stars we see today weren't always nearby and won't always remain. Everything is in motion, quietly, slowly, endlessly. The constellations our ancestors mapped, the patterns they saw in the night sky are temporary arrangements. In another galactic year, the sky will look utterly different. The sun bobs up and down through the galactic plane as it travels, oscillating above and below the disk like a horse on a carousel, moving through different densities of stars, different concentrations of cosmic dust, different levels of background radiation. Some researchers have even wondered whether this motion might correlate with cycles of mass extinction on Earth. The theory suggests that when the solar system passes through the galactic plane, where matter is more densely concentrated, it might disturb the Oort cloud at the edge of our solar system, sending comets raining down into the inner solar system, some of which could impact Earth. The evidence is controversial and far from certain, but it's a haunting thought that our motion through the galaxy might influence the evolution of life on our planet in ways we're only beginning to understand. Even as we sleep, the Earth turns, the Moon circles, and the entire solar system sweeps forward through a galaxy in motion, carrying us through space at speeds that would traverse the entire continental United States in less than 15 seconds. The galaxy is still growing. Although the Milky Way is ancient, formed over 13 billion years ago in the early universe, it isn't finished. Even now, it continues to gather material, gas from the intergalactic medium, stars from captured dwarf galaxies, and streams of dark matter that feed its halo. It grows not like a living thing, but like a gravitational structure deepening over time, an accumulation of matter drawn together by the inexorable pull of gravity. Some of this growth happens quietly through infalling clouds of primordial gas slipping into the disk, where they'll eventually condense into new generations of stars. Other times it comes with disruption, as satellite galaxies are torn apart and their stars scattered across the sky, absorbed into the Milky Way's halo and disk. The galaxy you live in today is not the same one the dinosaurs saw, and the one your distant descendants may know, if any exist, could be larger still, stitched from the ruins of 1,000 smaller worlds. This ongoing growth is one of the most fascinating aspects of galactic evolution. The Milky Way doesn't exist in isolation, sealed off from the rest of the universe. Instead, it's embedded in a cosmic web of filaments, vast rivers of gas and dark matter that flow through the space between galaxy clusters like blood vessels through a body. Along these filaments, fresh hydrogen streams into the Milky Way, providing the raw material for new generations of stars. Some of this gas arrives cold, at temperatures of just a few tens of degrees above absolute zero, slipping quietly into the disk where it will eventually condense into molecular clouds. Other streams fall in hot, shock-heated to millions of degrees by their rapid infall, visible only in X-ray and ultraviolet light, announcing their arrival with brilliant flares of energy. Dwarf galaxies continue to wander into the Milky Way's gravitational embrace, some of them containing only a few million stars, others rich in dark matter but nearly devoid of visible light, ghost galaxies made mostly of substance we cannot see. Each one that falls in adds to the Milky Way's mass, to its complexity, to its evolving story. The galaxy is not a static structure, but a living, growing entity, constantly fed by the cosmic web that surrounds it. We don't know how many arms the Milky Way has. It seems like something we should know, how many major spiral arms spiral from the center of our own galaxy. But from our position deep inside the disk, 26,000 light-years from the center, it's extraordinarily hard to see the whole structure. Dust clouds obscure distant regions, absorbing visible light and making it impossible to see what lies beyond. Stars blur into one another when viewed from within the disk, their light overlapping and merging into a continuous glow. For decades, astronomers believed there were 4 major spiral arms based on young stars and gas clouds. More recent observations, using infrared and radio telescopes that can peer through the dust, suggested maybe fewer, perhaps only 2 major arms with several smaller segments, or that the arms twist and split in ways more complex than expected, fragmenting and reforming as they spiral outward. Some segments fade into diffuse regions. Others wrap around unexpectedly, connecting in ways that don't fit our models. The Milky Way may not be a neat pinwheel at all, but a living, layered swirl of stars shaped by forces we still don't fully understand. Some astronomers now think it might be what's called a flocculent spiral, with short, fragmentary arms rather than grand, sweeping structures. The truth is, we're still learning the basic architecture of our own home. It's humbling, really. We can map distant galaxies in exquisite detail, but our own galaxy remains partially mysterious, hidden from us by our position within it. This uncertainty speaks to how difficult it is to map our own galaxy from the inside. Imagine trying to draw a detailed map of a vast forest while standing in the middle of it, surrounded by trees in every direction, with fog obscuring everything beyond a few hundred meters. That's essentially what astronomers face. Different wavelengths of light reveal different features. Optical light shows young, bright stars. Infrared penetrates the dust to reveal cooler stars and gas. Radio waves trace the distribution of hydrogen. Each wavelength tells a slightly different story, and reconciling them all into a coherent picture remains one of the great challenges of galactic astronomy. Rogue stars are flung from the core at impossible speeds. Most stars drift calmly through the galaxy in relatively stable orbits, but a rare few are flung outward at astonishing speeds, fast enough to escape the Milky Way entirely and journey into intergalactic space. These are called hypervelocity stars, and they're some of the most fascinating objects in the galaxy. Some are the remnants of binary systems disrupted by the supermassive black hole at the center of the galaxy, torn apart by tidal forces so intense they defeat gravity itself. Here's how it works. When a binary star system ventures too close to Sagittarius A, the supermassive black hole at the galaxy's heart, the intense gravitational field pulls harder on the closer star than on its companion. This difference in gravitational pull, called a tidal force, can tear the binary apart with violent efficiency. One star falls into a tight orbit around the black hole or is consumed entirely, vanishing beyond the event horizon. The other star absorbs the orbital energy of the disrupted system and is slingshot outward, hurled into the dark at over 1,000,000 kilometers per hour, sometimes reaching speeds of up to 700 kilometers per second. These rogue stars travel alone, far from the galactic plane, like glowing comets with no return trajectory. They remind us that even in a galaxy bound by gravity, there are moments of violent release, quiet expulsions that send stars flying into intergalactic night, never to return. Some of these stars have been found racing through the galactic halo at speeds exceeding the Milky Way's escape velocity by significant margins. They will spend eternity drifting through the space between galaxies, solitary wanderers carrying with them the only light for millions of light years in any direction. Imagine being a planet orbiting such a star, if such planets exist. You would watch your home galaxy slowly shrink behind you over millions of years, dwindling from a vast spiral dominating the sky to a faint smudge of light among countless others, knowing that you're traveling away from it faster than any natural process could ever bring you back. Your star has been permanently exiled from its birthplace, condemned to wander the cosmic void forever. The Milky Way and Andromeda are on a collision course. High above the horizon on autumn nights, visible even to the naked eye as a faint blur, lies the Andromeda galaxy, a spiral much like our own, lying over 2 million light-years away. And yet, despite this vast distance, it is moving steadily toward us, approaching at about 110 kilometers per second. In about 4.5 billion years, these two giants of the local group will collide in what may be the most dramatic event this corner of the universe will witness. It won't be violent in the way you might imagine, no stars smashing into each other like billiard balls. Stars are so far apart that even when two galaxies completely interpenetrate, direct collisions between stars are almost impossibly rare. But the gravitational effects will be spectacular. The two galaxies' gravity will warp both into long, stretching arcs. Tidal tails, hundreds of thousands of light years long, will curl outward into space, beautiful and terrible. The supermassive black holes at each galaxy's center, Sagittarius A at 4 million solar masses, and Andromeda's central black hole at perhaps 100 million solar masses, may eventually spiral together, releasing gravitational waves so powerful they'll ripple through the fabric of space-time itself, distorting the geometry of the universe as they merge. Computer simulations show that the merger will likely take several billion years to complete, with the two galaxies passing through each other multiple times, their shapes becoming more and more distorted with each passage, until finally they settle into a single larger elliptical galaxy. Gas clouds will collide and compress, triggering tremendous bursts of star formation. The night sky, if anyone is around to see it, will be ablaze with millions of young, brilliant stars being born from the compressed gas. It will be a slow, elegant dance visible across billions of light years. The future of our home, written across the stars in gravity and light. Some stars orbit backward through the galaxy. Most stars in the Milky Way orbit the center in the same general direction, following the overall rotation of the disk, but not all follow the rules. Some stars, especially in the outer halo, move in retrograde, orbiting opposite to the galaxy's main rotation, swimming upstream against the flow. These stars likely arrived from elsewhere, born in dwarf galaxies that were later absorbed by the Milky Way, their original orbital motion preserved, even as their home galaxy was torn apart. Their reversed motion is a quiet signature of their foreign origin, a clue written in velocity. It's as if the galaxy carries old memories in its motion, stories of ancient mergers and cosmic encounters preserved not in light, but in the slow, patient turning of stars against the stream. Each retrograde star is a witness to a violent event in the galaxy's past, a merger or collision that happened so long ago that all other evidence has faded, leaving only these wayward stars as testimony. By carefully mapping these retrograde stars and analyzing their orbits, astronomers can reconstruct the paths of the dwarf galaxies they came from, piecing together a history of ancient collisions and mergers that shaped the Milky Way. It's like forensic astronomy, using present-day evidence to solve mysteries billions of years old. Each backward-moving star is a clue, a fragment of a story that began before the Sun and Earth existed. The Milky Way may have eaten dozens of dwarf galaxies over its lifetime. Over billions of years, the Milky Way has not grown alone through quiet accumulation. It has consumed other galaxies. Small galaxies, faint luminous companions, have drifted too close, been caught in the Milky Way's gravity, and slowly dismantled, torn apart by tidal forces until nothing remains but scattered stars. Their stars are now part of our halo, disk, or stellar streams, assimilated completely. Astronomers have identified several of these mergers by analyzing stellar motion and composition, looking for groups of stars that move together and share similar chemical fingerprints. One especially large event, the Gaia-Enceladus merger, occurred about 10 billion years ago and added many stars to the Milky Way. It may have fundamentally reshaped the early structure of the galaxy, puffing up the disk and creating what we now call the thick disk, a layer of older stars that extends above and below the main galactic plane. The Milky Way is not a pristine spiral that formed smoothly and has remained undisturbed. It is a composite, a patchwork built from quiet collisions and violent mergers, stitched together from the remains of many smaller worlds. Every merger adds complexity, enriches the chemical composition, and reshapes the structure. The galaxy is a palimpsest, with older structures visible beneath newer ones, if you know how to look. The chemical makeup of stars reveals their origin like a fingerprint. Every star carries a unique chemical fingerprint, a pattern of elements imprinted at its birth that remains throughout its lifetime. By studying these signatures through spectroscopy, splitting starlight into its component wavelengths, and analyzing the absorption lines, astronomers can trace a star's history with remarkable precision. Some stars are rich in heavy elements like iron, calcium, and magnesium, suggesting they formed in dense, metal-rich regions where previous generations of stars had already lived and died, enriching the gas with their stellar ash. Others are nearly pure hydrogen and helium, born when the universe was still young and pristine, before supernovae had time to seed the cosmos with heavy elements. These differences allow scientists to group stars into families, uncovering ancient mergers and reconstructing the hidden story of the Milky Way's formation. Stars from dwarf galaxies that were absorbed long ago have different chemical patterns than stars born in the Milky Way itself. By mapping these patterns across the galaxy, astronomers can identify which stars came from where, tracing the galaxy's merger history written in stellar compositions. In this way, chemistry becomes a kind of time machine, letting us read a star's past like a line of ancient poetry written in light. Each absorption line in a spectrum tells a story: where the star was born, what materials were available at that time, what events had occurred in the universe before that star ignited. The universe preserves its history in the atoms that make up stars, and we're learning how to read that history. The sky is full of stellar streams from shredded galaxies. Across the sky, invisible to the naked eye but unmistakable when mapped with precision instruments, thin ribbons of stars stretch in arcs and curves. These are stellar streams, the remnants of smaller galaxies that wandered too close to the Milky Way and were pulled apart by tidal forces, stretched and torn until their stars were smeared across space. As they orbit, their stars are drawn out into long, delicate trails that trace their former paths like cosmic contrails. Some streams wrap around the galaxy like ghostly halos, invisible loops of stars marking the death throes of dwarf galaxies. Others dive in toward the core, their stars mingling with the Milky Way's native population, becoming indistinguishable over time. These streams are evidence of past collisions, quiet mergers that built the Milky Way over billions of years through cosmic cannibalism. The galaxy, like a tree, carries the rings of its past in every thread of light, every stream a chapter in its history. One of the most spectacular is the Sagittarius stream, which wraps completely around the Milky Way, looping above and below the disk in a complex, intertwining pattern. It's the tattered remains of the Sagittarius dwarf galaxy, which is still in the process of being consumed, still dying even as we watch. With each orbit around the Milky Way, more stars are stripped away, stretched out along its path, until eventually there will be nothing left but a diffuse stream of stars marking where the galaxy once orbited. But streams aren't just archaeologically interesting. They're also powerful tools for mapping the distribution of dark matter in the galaxy. The precise shape of a stream depends on the gravitational field it's moving through. And by carefully mapping streams and analyzing their trajectories, astronomers can infer the distribution of dark matter in the Milky Way's halo. These faint ribbons of stars act like test particles, revealing the invisible architecture that holds the galaxy together. The Milky Way is warped like a bent disk. Our galaxy doesn't lie flat like a perfect spiral in a textbook diagram. Its disk bends upward on one side and downward on the other, forming a graceful wave across the stars, like a vinyl record that's been left in the sun. This subtle warp was invisible to us until radio telescopes mapped the distribution of hydrogen gas that extends far beyond the visible starlight, revealing the galaxy's true three-dimensional shape. Astronomers believe the distortion may be caused by satellite galaxies tugging gently on the Milky Way's edges, or by clumps of dark matter bending the structure from below, like hands pressing on a sheet. Recent observations suggest the warp might even be dynamic, not static, precessing slowly, rotating around the galaxy's center like a wobbling plate. The Magellanic Clouds, two small satellite galaxies visible from the southern hemisphere, may be partly responsible, their gravitational influence twisting the outer disk as they orbit. Like ripples in a great spinning sheet, the warp reveals that even galaxies are never fully still, never perfectly formed. Over time, they bend, flex, and change shape in response to invisible forces, responding to every gravitational perturbation. From a distance, the Milky Way might look like it's dancing slowly through space, its disk undulating gently as it turns, a cosmic ballet choreographed by gravity. You can only see about 0.00003% of the Milky Way with the naked eye. Under a clear, dark sky, far from cities and streetlights, blessed with perfect atmospheric conditions, you might see a few thousand stars with your unaided eyes. To the human eye, that seems like an ocean of light, an overwhelming abundance. But it's barely a droplet. The Milky Way contains over 100 billion stars, possibly as many as 400 billion. Most are completely hidden from view, invisible to human sight. Some stars lie behind thick curtains of interstellar dust that absorb their light completely, blocking them as effectively as a brick wall. Others are too faint or too far away for our vision to reach. Red dwarfs that barely glow, or distant giants whose light has dimmed to near nothing by the time it reaches Earth. The pale streak of the Milky Way that crosses the sky on moonless nights, that band of light that ancient peoples called the Milk Road or the Silver River, is just the innermost whisper of the whole, just the densest part of the disk where enough stars overlap in our line of sight to create a visible glow. We live surrounded by a colossal river of starlight, embedded in a galaxy so vast that even traveling at the speed of light, it would take 100,000 years to cross from one side to the other. And yet almost all of it remains invisible to us, too vast to grasp from within, too distant to see, too obscured by dust to perceive. The stars we can see are almost all within a few thousand light-years of the Sun, a tiny bubble of visibility that encompasses perhaps 1/10,000th of the galaxy's volume. Beyond that bubble, billions upon billions of stars shine unseen, their light blocked or simply too faint to trigger our retinas. Stars orbit the galaxy at different speeds, creating the spiral arms. Unlike planets in a solar system, which follow neat, orderly orbits dictated by a single massive center, stars in the Milky Way move with more freedom, subject to the combined gravitational pull of billions of other stars and the massive dark matter halo that surrounds everything. Some stars race ahead in the inner regions, whipping around the galactic center in relatively tight orbits. Others drift slowly along the outskirts, taking hundreds of millions of years to complete a single revolution. This difference in orbital speed is why spiral arms form. They're not solid structures made of specific stars rotating together like the arms of a pinwheel. If they were, differential rotation would wind them up tighter and tighter over time until they twisted into an impossibly tight spiral and disappeared. Instead, they're patterns, waves of density, like slow traffic jams of stars and gas moving through space. As these density waves pass through the disk, they compress gas clouds, and that compression triggers star formation. The spiral arms move at what's called the pattern speed, which is different from the speed of the stars themselves. Stars drift into the arms, slow down slightly as they pass through the denser region, lighting up as new stars form around them, then speed up again as they leave. The arms themselves persist because they're continuously replenished with new material. As one generation of stars drifts out, another enters from behind, maintaining the pattern. Our own sun is part of this swirl, moving in and out of spiral arms across galactic time. It likely passes through a spiral arm every few tens of millions of years, spending most of its time in the quieter inter-arm regions. Right now, we're in the Orion Spur, a minor spiral feature between the larger Sagittarius and Perseus arms. The galaxy is not a clock, rigid and regular. It is a current, and we are drifting in it, carried along by forces too vast to resist. The galaxy holds together because of something we cannot see. By all logic, by all the mathematics of Newtonian gravity, the Milky Way should not exist in its current form. Based on what we can measure, the visible stars, the gas, the dust, everything that emits or absorbs light, the outer edges of the galaxy are spinning too fast. They should be flung into space, scattered like drops of water from a spinning wheel. The gravity from visible matter alone is not nearly enough to hold them in place, and yet they remain, orbiting serenely, bound to the galaxy by forces we don't fully understand. The answer, or at least part of it, is dark matter. This mysterious substance does not shine, does not reflect light, does not emit radiation in any wavelength we've detected. It doesn't interact with electromagnetic forces at all, as far as we can tell, but it exerts gravity, lots of it. And there is so much dark matter that it outweighs all the visible matter in the galaxy many times over, perhaps by a factor of 6 or more. We don't know what dark matter is. We don't know what particles it's made of, how it formed, or why it exists, but we know that without it, the Milky Way would fly apart. Galaxies would never have formed in the early universe. The cosmic web that connects galaxy clusters would not exist. Dark matter is the invisible scaffolding that holds not just the Milky Way, but the entire universe together, the hidden architecture beneath all visible structure. Astronomers detect dark matter not by seeing it directly, by definition it's invisible, but by watching how it moves other things. Stars at the edge of the galaxy orbit faster than they should based on visible matter alone, implying additional mass we can't see. Gravitational lensing, the bending of light around massive objects, reveals concentrations of matter where there are no visible stars or gas. The rotation curves of spiral galaxies remain flat far beyond the visible disk rather than declining as they should, telling us that mass continues to exist even where we see nothing. It is the galaxy's hidden scaffolding, invisible, silent, and still one of the greatest mysteries in science. Billions of dark matter particles are passing through your body right now, every second, moving at hundreds of kilometers per second, and they pass through without leaving any trace because they barely interact with ordinary matter at all. We are swimming in a sea of dark matter, embedded in it, surrounded by it, and yet we cannot see it or touch it. Understanding what it is remains one of the grand quests of modern physics. There's a supermassive black hole at the core, and it's been quiet for far too long. At the very center of the Milky Way, hidden behind thick clouds of gas and dust that make it invisible in optical wavelengths, lies an enormous black hole, a singular point of gravity so intense that not even light can escape it. This monster is called Sagittarius A*, and it is more than 4 million times the mass of the Sun, yet it occupies a space smaller than the orbit of Mercury. It's a paradox of cosmic proportions, enormous mass compressed into a vanishingly small volume. We cannot see Sagittarius A* directly. It's a black hole, after all, invisible by definition. But we've watched nearby stars whip around it at tremendous speeds, tracing invisible ellipses through the void, their orbits revealing the presence of something massive and dark. One star, designated S2, orbits so close that it reaches speeds of up to 5,000 kilometers per second, nearly 2% the speed of light at its closest approach. By tracking S2 and other stars in the galactic center with exquisite precision over decades, astronomers have been able to determine that there must be a concentration of more than 4 million solar masses in a region no larger than our inner solar system. Sometimes gas and dust fall inward toward Sagittarius A* and flare with X-rays as friction heats them to millions of degrees before they spiral into the event horizon and vanish forever. But these flares are relatively modest. For now, Sagittarius A* sleeps, or at least slumbers quietly, accreting material at a very low rate. But long ago, perhaps just a few million years ago, it may have been far more active. It may have burned like a quasar, a brilliant, violent beacon fueled by massive infall of matter, shining so brightly that it would have been visible across billions of light years. Evidence for this past activity comes from the Fermi bubbles, enormous lobes of gamma-ray emission extending tens of thousands of light years above and below the galactic plane, likely blown out by intense radiation and winds from the central black hole during a period of violent feeding. If the Milky Way's heart were feeding as actively as some other supermassive black holes we observe in distant galaxies, it would outshine every star in the galaxy combined. It is the silent conductor of the Milky Way's heart now, pulling stars into slow, relentless dance, waiting, perhaps, for the next major infall of matter to wake it from its slumber. The Milky Way has a peanut-shaped bulge that defies simple explanation. When astronomers mapped the center of the galaxy using infrared light that can penetrate the obscuring dust, they discovered something unexpected and strange. The central bulge is not a smooth, round ball of stars like you might expect from a simple spiral galaxy. Instead, it's a three-dimensional peanut-shaped, or perhaps more accurately described as a box or X-shaped when viewed edge-on. Seen from the side, it swells in the middle and narrows at the ends like a twisting hourglass made of hundreds of millions of stars. This strange geometry likely formed from the galaxy's central bar, a dense stripe of stars that rotates slowly through the center, buckling and puffing upward over time due to vertical instabilities. As the bar rotates, stars develop vertical motions, oscillating up and down out of the plane of the disk. Over billions of years, these vertical oscillations build up, creating a bulge that's thicker in the vertical direction, giving it that characteristic peanut or box shape. These inner structures are sculpted by gravity, billions of years of motion, and the accumulated rhythm of stellar orbits following paths so complex they can only be understood through computer simulations. We live in a spiral galaxy, everyone knows that, but its heart is full of complexity, not flat or clean or simple, but intricate and alive, shaped by dynamics we're still working to fully understand. The peanut bulge is a reminder that galaxies are not static structures, but dynamic systems, constantly evolving, constantly surprising us. Stellar nurseries shape the spiral arms with the birth of stars. The Milky Way's spiral arms are not simply made of stars, though that's what we see when we look at them. They're woven from the birthplaces of stars, from the raw material of creation itself. Giant clouds of molecular hydrogen, dust, and complex molecules drift through the galaxy, some of them spanning hundreds of light years across and containing the mass of millions of suns. And when these clouds pass through the spiral arms, they encounter the density wave, a region of enhanced gravity that compresses them. This compression is gentle by human standards, but powerful enough to overcome the internal pressure of the gas, causing it to collapse. As it collapses, it fragments into smaller clumps, and these clumps begin to form stars. These regions are called stellar nurseries, and they're chaotic, glowing, and full of motion. Young, hot stars, massive blue giants living fast and dying young, flood the surrounding gas with intense ultraviolet radiation, ionizing it and making it glow with a characteristic reddish color. Ultraviolet light from new stars lights up the clouds, painting the arms with radiant blues and silvers, creating the brilliant spiral pattern we see in images of the galaxy. These bursts of creation trace out the spiral shape, illuminating the curves of the galaxy with quiet fire. But the process is violent and turbulent. Stellar winds from young, massive stars and shock waves from supernovae carve bubbles and cavities in the molecular clouds, stirring the gas, compressing nearby regions, and triggering new rounds of star formation in a chain reaction that ripples through the spiral arms. Every star, even the sun, was born from one of these cloudy cradles long ago, 4.5 billion years ago in some forgotten molecular cloud that has long since dispersed. The atoms that make up your body were once part of such a cloud, enriched by previous generations of stars, waiting in the cold and dark for the compression that would ignite a new sun and begin the story of our solar system. The Magellanic Clouds are irregular satellites slowly being consumed. If you travel south of the equator and look up on a clear night, You might see two hazy patches of light hanging in the sky, like cosmic clouds frozen in place. These are the Large and Small Magellanic Clouds, two irregular dwarf galaxies that orbit the Milky Way. They're visible to the naked eye, companions to our galaxy that have followed us through space for billions of years. But they won't be with us forever. The Magellanic Clouds are being slowly consumed by the Milky Way's gravity. As they orbit, tidal forces stretch and distort them, pulling streams of gas and stars away from their cores. The Magellanic Stream, a vast ribbon of hydrogen gas stretching halfway around the sky, trails behind the clouds like a cosmic tail, marking their path through space. This stream contains enough gas to form 100 million new stars, slowly bleeding away from the dwarf galaxies as they spiral inward. Recent observations suggest the clouds may not actually be in stable orbits. Instead, they might be on their first passage close to the Milky Way, falling in from the depths of intergalactic space. If this is true, then what we're witnessing is their death spiral, a slow dance that will eventually end with them being torn apart and absorbed completely. In a few billion years, the Magellanic Clouds may no longer exist as distinct galaxies, their stars scattered across the Milky Way's halo, another chapter in the endless story of galactic cannibalism. For now, they remain, hanging in the southern sky, irregular and beautiful, companions in the night whose days are numbered. Globular clusters are ancient cities of stars. Scattered through the halo of the Milky Way, far above and below the galactic disk, are remarkable objects called globular clusters. These are dense, spherical collections of stars, some containing hundreds of thousands or even millions of stars packed into a region just tens of light years across. They're among the oldest objects in the galaxy, formed over 12 billion years ago when the universe was still young and the Milky Way was just beginning to take shape. Looking at a globular cluster through a telescope is like looking back in time. The stars are old, red, and metal-poor, born from gas that had been enriched by very few previous generations of stars. They orbit the galactic center in long, elliptical paths that take them far out into the halo and then plunging back down through the disk, following orbits that were established billions of years ago. What's remarkable about globular clusters is their density. In the core of a typical cluster, stars are packed so closely together that if you were standing on a planet orbiting one of those stars, your night sky would be ablaze with thousands of stars brighter than Venus appears from Earth. There would be no true darkness, just a perpetual twilight filled with countless brilliant points of light. The gravitational interactions between these densely packed stars can be violent. Close encounters can fling stars out of the cluster entirely or cause binary systems to merge in brilliant stellar collisions. The Milky Way has about 150 known globular clusters, but there may be more hidden behind dust clouds or lurking in the far reaches of the halo. Each one is a time capsule, preserving conditions from the early universe, a fossil record of the galaxy's youth. They remind us that the Milky Way is old, that it has been turning through space for so long that entire stellar populations have lived and died multiple times over. Neutron stars and pulsars keep cosmic time with impossible precision. Scattered throughout the Milky Way are some of the strangest objects in the universe: neutron stars, the collapsed cores of massive stars that exploded as supernovae. When a star runs out of fuel and can no longer support itself against gravity, its core collapses in a catastrophic implosion, compressing matter to densities so extreme that protons and electrons are crushed together into neutrons. The result is a sphere just 20 kilometers across, but containing. The most astonishing thing about pulsars is their precision. The best pulsars keep time more accurately than atomic clocks. Their rotation so stable that they pulse with a regularity that varies by less than a microsecond over decades. Astronomers use them as cosmic clocks, timing their pulses to study gravitational waves, test theories of gravity, and even search for planets orbiting these stellar remnants. And yet, despite their precision, pulsars are violent objects. Their magnetic fields are trillions of times stronger than Earth's, strong enough to warp the quantum vacuum itself. Near the surface, matter behaves in ways that have no terrestrial equivalent, forming crystalline crusts of iron nuclei floating in a sea of electrons, with a superfluid core of neutrons flowing without friction beneath. Some pulsars are in binary systems with companion stars, slowly consuming matter from those companions in a process called accretion. As matter spirals down onto the neutron star, it heats to millions of degrees and emits powerful X-rays. These systems are cosmic laboratories, places where matter and energy behave in extremes we can barely comprehend, testing the limits of physics in conditions we can never recreate on Earth. Supernovae forge the elements and enrich the galaxy. Everything around you, everything you're made of, every atom in your body except for hydrogen was created inside a star. The carbon in your cells, the calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in the nuclear furnaces of stars that lived and died long before the sun was born. Most of this creation happens quietly over billions of years as stars fuse lighter elements into heavier ones in their cores. But the heaviest elements, the ones beyond iron in the periodic table, require conditions so extreme that they can only be created in the final, violent moments of a star's life. When a massive star exhausts its fuel, it collapses and then explodes in a supernova, a detonation so powerful it can briefly outshine an entire galaxy. In those final seconds, as the star tears itself apart, temperatures and pressures become so extreme that fusion can create elements all the way up to uranium and beyond. These newly created elements are blown out into space at tremendous speeds, enriching the interstellar medium with the raw materials for new generations of stars and planets. Every supernova is a moment of creation and destruction, death and rebirth, scattering the ashes of one star to seed the birth of countless others. The Milky Way has witnessed billions of supernovae over its lifetime. Some were so close that ancient humans may have seen them, brilliant new stars appearing in the sky where none had been before, shining for weeks or months before fading away. Chinese astronomers recorded several such events, including a supernova in the year 1054 that created the Crab Nebula, a glowing cloud of expanding debris that we can still see today. Without supernovae, the universe would be a simpler, emptier place. There would be no rocky planets, no complex chemistry, no life. We are, quite literally, made of stardust, assembled from elements that were forged in stellar explosions billions of years ago, scattered across space, and eventually gathered together to form the sun, the earth, and everything living on it. Brown dwarfs blur the line between stars and planets. Not everything that forms from a collapsing gas cloud becomes a star. Some objects, called brown dwarfs, are too massive to be planets, but too small to sustain the hydrogen fusion that powers true stars. They fall into a strange middle ground, neither fully stellar nor planetary, objects that glow faintly from the heat of their formation, but slowly cool over billions of years. Brown dwarfs can be anywhere from about 13 to 80 times the mass of Jupiter. Below 13 Jupiter masses, they're essentially just large planets. Above 80 Jupiter masses, they have enough mass to ignite hydrogen fusion and become true stars. But in between, they exist in a twilight state, generating some energy through the fusion of deuterium and lithium, but never achieving the sustained hydrogen fusion that defines a star. They're remarkably common in the galaxy, possibly numbering in the billions, but they're extraordinarily difficult to detect. They emit almost no visible light, just faint infrared radiation from their residual heat. Many likely drift through interstellar space completely alone, rogue brown dwarfs ejected from their birth systems, wandering the galaxy as solitary objects cooler than a pot of boiling water. Some brown dwarfs have been found with planetary systems of their own, tiny worlds orbiting objects that are themselves barely more than planets. Others exist in binary systems with true stars, or even in binary pairs with other brown dwarfs. They represent a fascinating intermediate class of objects, helping astronomers understand the full spectrum of what can form from a collapsing cloud of gas. The coolest brown dwarfs discovered so far have surface temperatures lower than the boiling point of water, cold enough that water vapor condenses in their atmospheres and forms clouds. They're more like giant Jupiters than like the Sun, with striped cloud bands and possibly even weather systems, storms raging in atmospheres of methane and ammonia, lit only by the faint glow of infrared radiation. Binary and multiple star systems are more common than single stars. Our Sun is actually unusual in its solitude. Most stars in the Milky Way don't exist alone. They're part of binary systems, with two stars orbiting each other, or even triple and quadruple systems, with 3 or 4 stars locked in complex gravitational dances. In fact, more than half of all stars have at least one stellar companion. These systems can be remarkably diverse. Some binaries are so close that the stars nearly touch, orbiting each other in hours, their outer layers distorted into teardrop shapes by tidal forces. Matter can flow from one star to the other in streams, creating spectacular accretion disks and violent outbursts. Other binaries are so far apart that they take hundreds of thousands of years to complete a single orbit, their companion star appearing as just another bright point in the sky. If you were standing on a planet in a close binary system, you would have 2 suns in your sky. Depending on the orbital configuration, you might experience periods with 2 suns above the horizon, casting overlapping shadows in different directions, followed by brief nights when one sun sets while the other remains visible. In some configurations, true darkness might be rare or non-existent, your world bathed in continuous daylight from one sun or the other. Triple star systems are even more complex. Often they're arranged hierarchically, with a close binary pair orbited at a great distance by a third star, or occasionally with all three stars in unstable, chaotic orbits that slowly evolve over time. A few systems with 4 or even more stars have been discovered, intricate gravitational choreographies that seem impossible but persist for millions of years. These systems challenge our understanding of planetary formation. How can planets form and maintain stable orbits in systems where multiple stars are pulling in different directions? And yet, we've discovered planets in binary star systems, worlds orbiting both stars in what's called a circumbinary orbit, like Tatooine from Star Wars, but real, confirmed through careful observations. The universe, it turns out, is far more creative than we imagined. Red giants will eventually consume their inner planets. Stars are not eternal. They're born, they live, and eventually they die. For stars like the Sun, death comes slowly, across billions of years. As a star ages and exhausts the hydrogen in its core, it undergoes dramatic changes. The core contracts and heats up, while the outer layers expand enormously, swelling to hundreds of times their original size. The star becomes a red giant, cooler on the surface, but vastly larger in volume. When the Sun enters its red giant phase in about 5 billion years, it will expand beyond the orbit of Mercury and possibly beyond Venus. The inner planets will be engulfed by the Sun's outer atmosphere, their surfaces melting and vaporizing as they spiral inward through increasingly dense gas. Eventually, they'll be consumed entirely, vaporized and absorbed back into the star that they've orbited for billions of years. The Earth might survive this fate, though barely. As the Sun loses mass through stellar winds, the Earth's orbit will expand outward, possibly just enough to avoid being engulfed. But survival would be meaningless. The Earth's surface will have been baked to temperatures hot enough to melt rock. The oceans boiled away billions of years earlier. The atmosphere stripped away by intense solar radiation. Any remnant that survives will be a scorched, lifeless ball of rock, orbiting a dying star. These systems challenge our understanding of planetary formation. How can planets form and maintain stable orbits in systems where multiple stars are pulling in different directions? And yet, we've discovered planets in binary star systems, worlds orbiting both stars in what's called a circumbinary orbit, like Tatooine from Star Wars, but real, confirmed through careful observations. The universe, it turns out, is far more creative than we imagined. Red giants will eventually consume their inner planets. Stars are not eternal. They're born, they live, and eventually they die. For stars like the Sun, death comes slowly, across billions of years. As a star ages and exhausts the hydrogen in its core, it undergoes dramatic changes. The core contracts and heats up, while the outer layers expand enormously, swelling to hundreds of times their original size. The star becomes a red giant, cooler on the surface, but vastly larger in volume. When the Sun enters its red giant phase in about 5 billion years, it will expand beyond the orbit of Mercury and possibly beyond Venus. The inner planets will be engulfed by the Sun's outer atmosphere, their surfaces melting and vaporizing as they spiral inward through increasingly dense gas. Eventually, they'll be consumed entirely, vaporized and absorbed back into the star that they've orbited for billions of years. The Earth might survive this fate, though barely. As the Sun loses mass through stellar winds, the Earth's orbit will expand outward, possibly just enough to avoid being engulfed. But survival would be meaningless. The Earth's surface will have been baked to temperatures hot enough to melt rock. The oceans boiled away billions of years earlier. The atmosphere stripped away by intense solar radiation. Any remnant that survives will be a scorched, lifeless ball of rock, orbiting a dying star. Eventually, the Sun will shed its outer layers entirely in gentle pulses, creating a planetary nebula, a glowing shell of gas expanding outward into space. What remains of the core will collapse into a white dwarf, a dense, hot remnant about the size of Earth, but containing most of the Sun's original mass. This white dwarf will slowly cool over trillions of years, fading from white to yellow to red to eventually black, a cold cinder drifting through space. This is the fate awaiting most stars in the Milky Way. The galaxy is already full of white dwarfs, billions of them, remnants of stars that lived and died over the past 13 billion years. Some are still hot and bright, others have cooled to near invisibility. In the far future, when the last stars have burned out and the universe has grown cold and dark, these stellar remnants will be among the last objects remaining, cold and dead, but still orbiting, still downed to the galaxies they once illuminated. The galactic habitable zone may determine where life can exist. Not all parts of the Milky Way are equally hospitable to life. Too close to the galactic center, radiation levels are high, stellar densities are extreme, and the risk of catastrophic events like supernovae or gamma-ray bursts becomes significant. Too far out in the outer disk or halo, heavy elements are rare, making it difficult to form rocky planets with the complex chemistry needed for life. Somewhere in between is what astronomers call the galactic habitable zone, a region where conditions are just right, enough heavy elements to form planets, but not so much radiation and stellar activity that life would be constantly sterilized. The Sun orbits in what appears to be a favorable location, far enough from the center to avoid the worst hazards, but close enough that our neighborhood was enriched with heavy elements from previous generations of stars. But this concept remains speculative and controversial. We don't really know what conditions are necessary for life to emerge and thrive. Life on Earth evolved in environments we once thought were completely hostile. Deep ocean vents, acidic hot springs, frozen Antarctic lakes. Perhaps life is more resilient and adaptable than we imagine, capable of emerging anywhere there's liquid water and a source of energy. The search for life beyond Earth is one of the great quests of our time. We're looking for biosignatures in the atmospheres of exoplanets, listening for radio signals that might indicate technological civilizations, studying the moons of Jupiter and Saturn where liquid water oceans might harbor simple life. Every new discovery expands our understanding of what's possible, what's probable, and where we should look next. Are we alone in the Milky Way? The question hangs unanswered in the cosmic silence. With hundreds of billions of stars and potentially trillions of planets, it seems almost impossible that Earth is the only world where life emerged. And yet, despite decades of searching, we've found no definitive evidence of life beyond our planet. The Fermi paradox asks, if the galaxy is so vast and so old, where is everybody? Perhaps we're the first. Perhaps civilizations are common but short-lived. Perhaps we're looking in the wrong places or listening for the wrong signals. Or perhaps intelligence is simply vanishingly rare, a cosmic fluke that happened once in our galaxy's history and might never happen again? We don't know. We can only keep searching, keep wondering, and keep looking up at the stars. Cosmic rays bombard the Earth from deep space. The space between stars is not empty. It's filled with radiation, magnetic fields, and high-energy particles racing through the void at nearly the speed of light. These particles, called cosmic rays, are mostly protons and atomic nuclei accelerated to tremendous energies by violent events like supernovae, pulsars, and perhaps even more exotic sources we don't yet understand. When cosmic rays strike Earth's atmosphere, they create cascades of secondary particles that shower down to the surface. Every second, several cosmic rays pass through your body. Most are harmless, but over long timescales, cosmic ray exposure contributes to background radiation and may play a role in evolution by causing genetic mutations. Astronauts in space, beyond the protection of Earth's magnetic field and atmosphere, receive significantly higher doses of cosmic ray radiation, one of the major challenges for long-duration space travel. The most energetic cosmic rays are particles with energies millions of times greater than anything we can produce in particle accelerators on Earth. Where they come from remains a mystery. They're so energetic that they must have been accelerated by the most violent events in the universe, colliding black holes, the jets from active galactic nuclei, or processes we haven't discovered yet. Each one carries information about the extreme physics operating somewhere in the cosmos. The Milky Way is bathed in these cosmic rays, threading through its spiral arms, bouncing off magnetic fields, creating a diffuse glow of high-energy particles that fills the entire galactic volume. They're one more reminder that space is not empty or peaceful, but filled with invisible energies and particles racing through the dark. The interstellar medium is full of complex chemistry. The space between stars seems like it should be empty, a near-perfect vacuum, with just a few stray atoms of hydrogen drifting through the void. But look closer and you find something surprising: chemistry. The interstellar medium is not empty, but filled with a thin but complex mixture of gas and dust. And within that mixture, molecules form. Not just simple molecules like hydrogen gas, but complex organic compounds. Astronomers have detected more than 200 different molecules in space, including water, ammonia, methane, formaldehyde, ethanol, and even amino acids, the building blocks of proteins. In dense molecular clouds, where temperatures drop to just a few degrees above absolute zero, these molecules freeze onto tiny dust grains, building up icy mantles that can be several molecules thick. When these dust grains are exposed to ultraviolet radiation from nearby stars, chemical reactions occur on their surfaces, creating even more complex molecules. Eventually, these grains may be incorporated into forming planetary systems, delivering water and organic compounds to young planets. Earth's oceans and perhaps even the precursor molecules that led to life may have arrived this way, delivered by countless impacts of comets and asteroids that formed in the outer solar system. This interstellar chemistry suggests that the ingredients for life are common throughout the galaxy, formed not on planets, but in the vast spaces between stars, waiting to be gathered up by gravity and incorporated into new worlds. We are not just made of stardust, but of the molecular heritage of the interstellar medium, chemistry that began in the cold darkness between stars, billions of years before the sun was born. The local bubble is a cavity blown out by ancient supernovae. The Sun doesn't just orbit through the Milky Way's disk, it orbits through a specific neighborhood, a region of space that has been shaped by past events. Our local region, extending for hundreds of light years in every direction, is called the local bubble, and it's a cavity in the interstellar medium blown out by multiple supernovae that exploded in our vicinity sometime in the past 10 to 20 million years. These explosions swept the surrounding gas and dust outward, creating a hot, tenuous gas that the Sun now moves through. The local bubble is surrounded by denser regions and shell-like structures where the swept-up material has accumulated. New stars are forming along these dense shells, triggered by the compression from the ancient supernovae. Inside the bubble, conditions are different from the general interstellar medium. The gas is hotter, thinner, and ionized. The Sun has been inside the local bubble for much of its recent history, though it occasionally passes through denser regions as it oscillates up and down through the galactic plane. This bubble may have had effects on Earth's climate and evolution. Some scientists have suggested that increased cosmic ray exposure during passages through the dense edges of the bubble might influence cloud formation in Earth's atmosphere, though this remains highly speculative. What's certain is that our position in the galaxy, our local neighborhood, is not random, but shaped by past violence, by stars that died before the Sun was born. The Fermi bubbles hint at ancient galactic violence. In 2010, astronomers analyzing data from the Fermi Gamma Ray Space Telescope discovered something unexpected. Enormous lobes of gamma ray emission extending above and below the galactic plane. Each lobe spanning more than 25,000 light years. These structures, now called the Fermi bubbles, were completely unknown before this discovery. The bubbles appear to have been blown out from the galactic center by some powerful event, possibly an intense period of star formation or a feeding frenzy by Sagittarius A, the supermassive black hole at the galaxy's heart. The energy required to create these structures is staggering, equivalent to perhaps 100,000 supernovae exploding over a relatively short period, or the release of tremendous energy as matter fell into the central black hole. The bubbles are expanding outward at about 1 million kilometers per hour, though at this speed they're still moving relatively slowly on cosmic timescales. Their sharp edges and uniform structure suggest they were created in a single event or a series of closely spaced events sometime in the past few million years, yesterday in galactic terms. They raise tantalizing questions. Was our galaxy once far more active than it is today? Could Sagittarius A have gone through a quasar phase in the relatively recent past? What triggered such an enormous energy release? And are there other hidden structures in the galaxy that we haven't detected yet, written in wavelengths we haven't looked at carefully enough? The Fermi bubbles remind us that the Milky Way has a history of violence, periods of intense activity that reshape its structure. The quiet galaxy we observe today may be just a lull between storms. Molecular clouds are the birthplaces of stars. Scattered throughout the Milky Way's spiral arms are enormous structures called giant molecular clouds, some of the largest and most massive objects in the galaxy. They're called molecular clouds because they're cold and dense enough that hydrogen atoms have combined into molecular hydrogen, H2, the most common molecule in the universe. Inside these clouds, the temperature drops to about 10 degrees above absolute zero. At these frigid temperatures, molecules can survive and complex chemistry can occur. Dust grains provide surfaces where molecules can meet and react, building up increasingly complex compounds. The clouds are so dense that they block out all visible light, creating dark nebulae where almost nothing can be seen. But infrared and radio telescopes can peer through the dust, revealing the intricate structures within. The clouds are not uniform, but filled with tendrils, clumps, and filaments shaped by turbulence, magnetic fields, and the gravity that slowly pulls them together. Some regions are collapsing, growing denser and hotter on their way to becoming stars. Others remain diffuse, waiting for the trigger that will start their collapse. These are the nurseries of stars, the places where new suns are born. The Orion Nebula, one of the most famous and easily visible star-forming regions, is just a small part of a much larger molecular cloud complex. Inside it, thousands of stars are forming right now, emerging from the dust and gas, lighting up their surroundings with ultraviolet radiation and beginning their long lives as luminous objects. Every star in the galaxy was born in a place like this. The Sun, 5 billion years ago, emerged from a molecular cloud that has long since dispersed, its remnants scattered across the galaxy by stellar winds and supernovae. In another 5 billion years, stars being born today in the Orion Nebula will drift apart, and the cloud itself will be gone, consumed by the stars it created. The cycle continues endlessly. Gas clouds collapse to form stars. Stars live and die. Supernovae and stellar winds return gas to the interstellar medium. That gas cools and eventually forms new molecular clouds, and the process begins again, generation after generation, slowly converting the galaxy's hydrogen into heavier elements, slowly dimming as fuel is consumed, but continuing nonetheless. Open clusters are stellar siblings drifting apart. Unlike the ancient, tightly packed globular clusters, open clusters are loose collections of young stars born together from the same molecular cloud, still drifting through space in proximity to their siblings. They're much younger, typically just a few million to a few billion years old, and contain anywhere from a few dozen to a few thousand stars. The Pleiades, visible to the naked eye as a small, fuzzy cluster, is one of the most famous open clusters. It's about 100 million years old, young enough that its member stars are still hot, blue, and luminous. They formed together, emerging from the same collapsing cloud, and for now, they remain gravitationally bound to one another, moving through the galaxy as a group. But open clusters are not permanent. Over time, gravitational interactions with passing stars and giant molecular clouds gradually disperse them. Stars drift away one by one, their orbits around the galaxy diverging, until eventually the cluster disappears entirely as a recognizable structure. The stars that formed together become scattered across the galaxy, siblings separated forever, with no way to know they were once part of the same family. The Sun may have formed in an open cluster billions of years ago. If so, the stars that were born alongside it have long since dispersed, now orbiting in completely different parts of the galaxy. Some astronomers have tried to identify the Sun's siblings by looking for stars with similar ages, chemical compositions, and orbital paths, but the search is difficult. After 4.5 billion years of galactic motion, the Sun's siblings could be anywhere. Open clusters serve as natural laboratories for studying stellar evolution, because all the stars in a cluster formed at the same time from the same material, they differ only in their masses. By observing a cluster, astronomers can see stars at different stages of evolution all at once, the most massive stars burning bright and blue, medium-mass stars like the Sun in their prime, and the smallest stars just beginning their long, slow lives. Clusters also help us measure cosmic distances. By comparing the brightness of stars in a cluster with their known luminosities based on their types, astronomers can calculate how far away the cluster is. This technique, called main sequence fitting, has been crucial for building the cosmic distance ladder, the series of methods used to measure distances to increasingly remote objects in the universe. Watch an open cluster for long enough, across millions of years, and you would see it slowly dissolve, its stars spreading out like seeds on the wind, carrying with them the memory of their shared origin, but gradually becoming indistinguishable from the background population of the galaxy. Planetary nebulae are the beautiful death throes of sun-like stars. Despite their name, planetary nebulae have nothing to do with planets. They're glowing clouds of gas ejected by dying stars, expanding outward into space at tens of kilometers per second, illuminated from within by the hot stellar core that remains. The name comes from early telescopic observations when these objects appeared as small, round, and greenish, resembling planets like Uranus or Neptune. When a star like the Sun nears the end of its life, after billions of years of steady fusion, it begins to pulse and shed its outer layers in gentle waves. These expelled shells of gas drift outward, lit by intense ultraviolet radiation from the exposed stellar core. The result is one of the most beautiful sights in astronomy: intricate, colorful clouds in shapes ranging from simple spheres to complex hourglass structures, rings, and spirals. The colors come from different elements in the gas, each emitting light at characteristic wavelengths when energized by the central star. Hydrogen emits red, oxygen gives green and green-blue hues, nitrogen produces red and purple, and sulfur adds to the red spectrum. The resulting images, when captured by telescopes like Hubble, are breathtaking works of cosmic art. But these structures are fleeting by cosmic standards. A typical planetary nebula lasts only about 10,000 years before it disperses into the interstellar medium, becoming too faint to detect. The central star remains behind as a white dwarf, slowly cooling over billions of years, while the gas it once contained spreads outward, eventually mixing with other material to be recycled into future generations of stars. The Cat's Eye Nebula, the Ring Nebula, the Helix Nebula. These are all dying stars, captured in their final moments of visible glory before fading into darkness. One day, our sun will create its own planetary nebula, a last burst of light and color before settling into quiet extinction. From a distant vantage point, it might be beautiful. From Earth, if the planet still exists, it will be the end of everything we've ever known. Thousands of planetary nebulae float through the Milky Way, each one the tombstone of a star, a memorial to billions of years of fusion, marking where a star once lived and died. They return their material to the galaxy, enriched with the heavy elements created during the star's lifetime, ready to be incorporated into new stars, new planets, perhaps new life. The mystery of the galaxy's missing satellite galaxies. According to our best computer models of how structure forms in the universe, the Milky Way should be surrounded by thousands of small satellite galaxies. But observations show we can only detect a few dozen. This discrepancy, known as the missing satellites problem, has puzzled astronomers for years. Several explanations have been proposed. Perhaps most of the predicted satellites are so small and dim that we simply can't see them with current telescopes. They might be there, hiding in the outer halo, too faint to detect. Or perhaps they're composed almost entirely of dark matter, with very few stars, making them effectively invisible except through their gravitational influence. Another possibility is that our models are wrong about how galaxies form, or about the nature of dark matter itself. If dark matter has properties different from what we assume, if it's warm rather than cold, or if dark matter particles can interact with each other in ways we haven't accounted for, it would change how small structures form and might explain why we see fewer satellites than predicted. Recent deep surveys have begun finding more ultra-faint dwarf galaxies, tiny collections of stars so dim they're barely detectable even with large telescopes. Each new discovery helps fill in the picture, but the total number found is still far below theoretical predictions. The gap remains. This problem connects to broader questions about the nature of dark matter and galaxy formation. Understanding why we don't see the predicted satellites could revolutionize our understanding of cosmology, or it could simply be a matter of looking more carefully with better instruments. Either way, it's a reminder that even our home galaxy still holds fundamental mysteries. The thick disk preserves the galaxy's violent past. When astronomers map the Milky Way's structure carefully, they find not one disk, but two. There's the thin disk, about 1,000 light-years thick, where most of the galaxy's gas and young stars reside. And there's the thick disk, extending several thousand light-years above and below the plane, populated by older stars with different chemical compositions and more chaotic orbits. The thick disk likely formed from violent events in the galaxy's past, perhaps from mergers with smaller galaxies that heated up the existing disk, puffing it up and scattering stars into higher orbits. The Gaia Enceladus merger, about 10 billion years ago, may have been responsible for creating much of the thick disk we see today. Stars in the thick disk are like archaeological artifacts, preserving information about conditions in the early galaxy. They're older, more metal-poor, and move on orbits tilted relative to the current galactic plane. Their presence tells us the Milky Way has not evolved smoothly, but has been shaped by catastrophic events, by collisions and mergers that fundamentally altered its structure. This layered structure, halo, thick disk, thin disk, is like a cross-section through time, with each layer representing a different era in the galaxy's history. The oldest stars in the halo formed first. The thick disk came next, built from mergers and violence, and the thin disk is the most recent, still actively forming stars, still evolving. By studying these different stellar populations, astronomers can reconstruct the Milky Way's history, piecing together a timeline of formation and evolution that spans nearly the entire age of the universe. The galaxy is not a simple static structure, but a complex layered system built up over billions of years, each layer telling part of the story. High-velocity clouds rain down on the disk. The space above and below the galactic disk is not empty, but filled with clouds of hydrogen gas moving at unusual velocities, sometimes approaching or receding from the disk at hundreds of kilometers per second. These are called high-velocity clouds, and while some are remnants of tidal streams from destroyed dwarf galaxies, others have more mysterious origins. Some high-velocity clouds appear to be falling into the disk, raining down from the halo like cosmic precipitation. They may be primordial gas left over from the galaxy's formation, only now falling in after billions of years in the halo. Or they could be gas expelled from the disk by supernova explosions and stellar winds, now falling back down after millions of years aloft, enriched with heavy elements from the stars that ejected them. When these clouds hit the disk, they don't fall gently. They crash in at high speed, creating shock waves that compress the gas in the disk and can trigger new bursts of star formation. Some regions of active star formation may have been initiated by the impact of high-velocity clouds, their infall providing the compression needed to overcome the gas's internal pressure and start gravitational collapse. The Smith cloud is one of the largest and most well-studied high-velocity clouds. It's on a collision course with the Milky Way's disk and will impact in about 30 million years. When it does, it could trigger the formation of millions of new stars in the region where it strikes, lighting up that part of the galaxy with new stellar nurseries. These clouds are another reminder that the galaxy is not a closed system. Material falls in from outside, mergers add new stars and gas, and the structure continues to evolve. The Milky Way is not finished forming. It's still growing, still changing, and will continue to do so for billions of years to come. The oldest stars tell us about the early universe. Within the Milky Way's halo orbit some of the oldest stars known, objects that formed when the universe was less than 1 billion years old. These stars are precious beyond measure to astronomers because they're the only direct samples we have of conditions in the very early universe. Their chemical compositions are extraordinarily simple compared to the Sun, where the Sun's atmosphere contains about 2% heavy elements by mass. These ancient stars contain less than 1/100th of 1%. They formed from gas that had been enriched by only the very first generation of stars, supernovae that exploded when the universe was just a few 100 million years old. By studying these stars, astronomers can learn about what those first stars were like. The pattern of elements in ancient stars tell us how massive the first stars were, how hot they burned, and how they died. Some ancient stars show unusual chemical signatures that suggest they were enriched by very specific types of supernovae, giving us clues about stellar evolution in the early universe. Finding these stars is challenging. They're rare, scattered throughout the halo in random orbits, and they're not particularly bright. Large sky surveys have helped identify candidates, which then must be followed up with detailed spectroscopic observations to confirm their ages and compositions. Each new discovery is an event, a window opening onto the earliest epochs of cosmic history. One star, HD 140283, contains so little iron that it may have formed from gas enriched by only a single supernova. It's like a message in a bottle, carrying information across 13 billion years about the death of one of the universe's first stars. Every ancient star is a fossil, a relic, a precious time capsule that somehow survived the chaos of galactic evolution to reach us today. The Milky Way's rotation curve reveals hidden mass. One of the clearest pieces of evidence for dark matter comes from measuring how fast objects orbit at different distances from the galactic center. According to Newton's laws, objects farther out should orbit more slowly, just as the outer planets in our solar system orbit more slowly than the inner ones. But that's not what we observe. When astronomers map the rotation velocities of stars and gas clouds throughout the Milky Way, they find something strange. The rotation curve, the plot of orbital velocity versus distance, remains flat far beyond the visible edge of the galaxy. Stars in the outer disk orbit just as fast as stars closer in. implying there must be additional mass far from the center, mass we cannot see. This invisible mass is what we call dark matter, and there must be enormous amounts of it extending far beyond the visible galaxy in what's called the dark matter halo. This halo may extend several 100,000 light-years from the galactic center, dwarfing the visible disk and containing perhaps 5 to 10 times more mass than all the stars, gas, and dust we can detect. Without this dark matter, the Milky Way would not exist in its current form. The outer regions would simply fly off into intergalactic space, unable to maintain their orbits. The spiral structure would unwind, the disk would disperse, and the galaxy would tear itself apart over just a few rotations. Dark matter's presence is undeniable based on its gravitational effects, yet we still don't know what it is. Countless experiments have searched for dark matter particles, looking for rare interactions with ordinary matter, but so far, none have made a definitive detection. It remains the galaxy's greatest invisible presence, the hidden foundation upon which everything visible rests. The bar at the galaxy's center rotates independently. Recent observations have revealed that the Milky Way is not a simple spiral galaxy, but a barred spiral, with a dense, elongated structure of stars running through its center. This bar is about 27,000 light-years long and rotates as a rigid structure, taking about 130 million years to complete one rotation. The bar's rotation is independent of the disk's rotation, creating a complex dynamic environment in the central regions of the galaxy. As the bar rotates, it creates resonances where its gravitational influence periodically compresses the disk, potentially triggering spiral arm formation and affecting the rate of star formation. Stars near the bar move on unusual orbits, some following elongated paths aligned with the bar, others moving perpendicular to it. The gravitational forces are strong and variable, creating a dynamic environment quite different from the relatively calm outer disk where we live. The bar may funnel gas toward the galactic center, feeding the central black hole and potentially triggering periods of higher activity. Computer simulations suggest bars can be long-lived stable structures, but they can also dissolve and reform, especially after major mergers. The Milky Way's bar may be billions of years old, or it could be a relatively recent feature, formed in the aftermath of a past galactic encounter. From our vantage point, 26,000 light-years away, we see the bar at an angle, tilted about 27 degrees from our line of sight. This makes it challenging to study directly, but infrared observations that penetrate the dust have mapped its structure in detail, revealing a complex peanut-shaped bulge connected to the bar, all rotating together through the heart of our galaxy.
And now we drift toward our ending, this gentle journey through cosmic mysteries. You've traveled far tonight, from the twisted spiral arms to the silent black hole at the center, from ancient stars born before the galaxy itself to the future collision with Andromeda billions of years hence. We've wandered through stellar nurseries where new suns are being born, and past planetary nebulae where old stars breathe their last. The Milky Way remains a place of mystery and wonder. Despite centuries of observation and decades of sophisticated space missions, we still don't know some of its most basic properties: how many spiral arms it has, exactly how much it weighs, what fraction of its mass is dark matter, how many stars it contains.
We live inside a cosmic structure we can barely map, surrounded by wonders we can scarcely comprehend. But perhaps that's fitting. Perhaps we're not meant to know everything all at once. The universe offers its secrets slowly, grudgingly, and that's what makes each discovery meaningful. Every answer leads to new questions. Every mystery solved reveals deeper mysteries beneath. As you drift off to sleep, remember that you're part of this vast cosmic story. The atoms in your body were forged in stars that exploded billions of years ago. You're traveling through space at hundreds of kilometers per second, orbiting a galactic center you'll never see with your own eyes. You're embedded in a structure 13 billion years old, living on a planet that has circled the galaxy only 20 times since it formed. The Milky Way is your home on the grandest scale. It's the collection of hundreds of billions of stars that provides the context for everything human civilization has ever accomplished. And it's still largely unknown, still mysterious, still waiting to reveal more of its secrets to those curious enough to look.
Rest now. Let the galaxy turn. Let the stars drift in their ancient orbits. Let the mysteries remain mysterious for another night. Tomorrow, if you wish, you can look up at the sky and know that you're looking at a galaxy from within, a spiral of light and darkness, of known and unknown, slowly turning through the cosmic night. Thank you for joining me on this journey through our home galaxy. May your dreams be filled with stars and your sleep be deep and peaceful. Until we meet again among the cosmic mysteries, good night.